So today we're going to talk about Experiment 7 again. This is part B video for the NMR. The last video series we were talking about how NMR works, so I gave you a brief introduction as to how we get NMR signals. I also related it to MRI a little bit, something that most people are somewhat familiar with. And we talked about proton NMR, the delta scale or the chemical shift, as well as splitting and integration, and then we went through some examples. In the current video, we're going to be talking about carbon-13 NMR, which is another important NMR technique that's available to chemists and organic chemists, particularly like this. And then after carbon-13 NMR, I'm going to talk about a problem-solving strategy that you can use to solve spectroscopy problems when given various pieces of information, including NMR. So we'll cover that as well. This is going to be a fairly long video relative to many of the others, and so make sure you've allotted enough time to watch all the sections of this video that we're posting. It's important to note that a sample of natural carbon, so just if you had a big pile of carbon, only about 1% of that is carbon-13. The rest of it's carbon-12. And carbon-13 is the only carbon atom that is actually NMR active that we're interested in. And so there's very little of it in our sample. And so carbon-13 is actually very insensitive, and it takes a long time to run a carbon-13 spectrum relative to a proton spectrum. So just as an example, you can run a proton NMR spectrum in about 2 or 3 minutes pretty easily. However, a carbon-13 sample that you want to run a spectrum on usually can take anywhere from 30 minutes to an hour at minimum. So we've already run these samples for you in lab. You'll have the printouts, and again, this is a dry paper lab where you'll come in and actually learn how to interpret these spectra, not necessarily how to run them. The information that we get from a carbon-13 NMR are the following. We get the number of unique carbon atoms, and I point out here in red, unique. It's not the total number of carbons. You're going to find the number of carbon signals as proportional to the number of unique carbon atoms, and so we'll talk about what we mean by that here in just a little bit. You can also get quite quickly by looking at the chemical shift what kind of hybridization the carbon's in. Is it an sp2 hybridized carbon? Is it an sp hybridized carbon? Or is it sp3? What you don't get in a carbon-13 NMR that you did get from proton NMR, we don't get integration. We don't integrate these signals, so you can't say this particular signal is due to 4 carbons, for example. And we don't see any splitting due to neighboring carbons or neighboring hydrogens. And this is a result of how the experiment is actually performed. It's not that you couldn't get this information. It's just that since carbon-13 is so insensitive, we run it in a special mode that gets rid of all of this integration and splitting patterns. And as a result, actually simplifies the spectrum quite a bit. So if we look at this example, this is methane, CH4. This is a single carbon, so we'd expect one signal. However, it does have 4 hydrogens attached to it. And so if those hydrogens split that carbon signal, we would expect 4 plus 1 to give us 5 signals. We would expect to see something that looks like this in the carbon-13 NMR spectrum for methane. However, because of the way the experiment is actually run, all we observe is a single peak, what we call a singlet. And so that really simplifies the NMR spectrum tremendously. When you look at an NMR spectrum, you're going to see a series of single lines on the spectrum that you have to pay attention to for that. So let's look at an example. And we're going to return to our iodo-propane example. And I'm going to label the carbons A, B, and C. And as you can see, there are, of course, 3 carbons that are contained in iodo-propane. So we would expect to see 3 carbon signals, because A is clearly unique from B and B is clearly unique from C. There's nothing that relates A to C or B to C or anything like that. They're all unique. Now, if we look at a carbon spectrum, what we'll see, very similar to what we saw for proton, we'll have a parts per million scale or a delta scale here on the x-axis, and we'll have the intensity on the y-axis. However, the scale is significantly expanded for carbon-13. For proton, we were talking anywhere from 0 to 10 to 12. For carbon, the scale goes from 0 parts per million to about 200 to 220 parts per million. And we're going to just kind of stick with the 200 part here, but sometimes we can get out to the 220. So it's a much greater scale. The signals are singlets and they're separated by a larger distance. It makes carbon-13 actually easy to interpret. So I'm going to split the spectrum here just a little bit, and we're going to focus here on the upfield region. And again, close to 0 is upfield, closer to 200 is known as downfield. And in this region for iodo-propane, we would expect to see 3 signals. And I'm using, again, an exaggerated scale so you can see it pretty easy. These signals are actually fairly close together. And what you would notice is that this one would be at about 9 parts per million. This one would be at about 12 parts per million. And then the last one would be at around 25 parts per million on the delta scale. Okay? 3 signals, 3 carbons. And now we need to assign these signals to the carbons. And it turns out, just like in proton NMR, if you're attached to an electronegative atom, that pulls the carbon signal further downfield. So we would expect A to be the furthest downfield. We would expect that to be the signal at 25 parts per million. B is further away from the electron withdrawing iodine, but it's closer than C. So we would expect B to be the next furthest downfield. And then we would expect C, of course, to be the furthest upfield. So we've got our 3 signals, A, B, and C. And so if anytime you have an electron withdrawing group, that's going to pull the signal in the downfield direction. And we'll be able to do that fairly easily by simple inspection here. So just by simple inspection of the spectrum, we can get a lot of information, just like we did by simple inspection of the proton signals last time. So let me go ahead and erase this. Expand this out just a little bit so we can have plenty of room to write what we need to write. So if we look at a typical carbon NMR, again, goes from about 0 parts per million to about 200. And just like in the proton NMR where we picked the midpoint and drew an imaginary line, we can do the exact same thing in carbon. So we go to the midpoint at about 100, and we're going to draw an imaginary line. Okay? Everything upfield of 100 is going to be either sp3 hybridized carbon atoms or sp hybridized carbon atoms, just like we saw for proton. sp3 hybridized hydrogens and sp hybridized hydrogens, or hydrogens attached to those types of carbon anyway, were on the right, and the sp2 hybridized carbons will be downfield from 100. So just by simple inspection, you can tell the number of carbon atoms that you have that are unique, and you can get an idea of what type of hybridization you have. So we would expect to see closer to 0 our sp3 hybridized carbon atoms, something like a methyl group, for example. Closer to 100, we would expect to see things like alkynes. We'd expect to see those carbons in this region. On the other side of 100, we would expect to see things like alkenes, aromatic rings. All of these carbons are sp2 hybridized. And as we get closer to 200, we would expect to see things like ketones and aldehydes. Those will appear pretty close to 200. And we would expect to see carboxylic acids and esters somewhere around 170 to 180 parts per million, so in this region. So this is kind of a rough diagram that you can use to kind of predict what type of carbon you have pretty easy. If you see stuff pretty close to 0, you know it's got to be sp3 hybridized. If it's still in this region but it's further downfield, it's got to be attached to some type of electronegative atom. If it's in this region, fairly close to 100, in the 70 to 80 region, you would expect to see sp hybridized carbons, things like alkynes. If it's just past 100, you'd expect to see alkenes and aromatic carbons, and then, of course, a little further down, you would expect to see carboxylic acids and esters, and the furthest down, we'd expect to see things like aldehydes and ketones. So just to remind here. Now, that's just by simple inspection. You do have a series of tables in your textbook and in your lab manual that will actually pinpoint these more accurately. So if it's an sp3 hybridized, but it's got 2 R groups on it, it's going to appear at a little different shift than something that only has 1 R group, like a methyl group. And so you can pinpoint those in pretty easily by looking at those tables that are both in your lecture text and your lab manual. However, again, this simple inspection tells us a lot of information without having to grab for a table at all. So let's actually predict an NMR spectrum based on an example.